what we have here is a picture of a galaxy, and the spectrum, or a piece of the spectrum, in the red range, around 600s, our wavelength nanometers is in the red range. Your eye really wouldn't be able to distinguish any intensities here, and this is showing intensity versus wavelength, and so there you would see this essentially as a bright red stripe in the in the spectrum, and that's due to hydrogen. And from this picture and from the spectrum, we're going to be able to and some assumptions, we're going to be able to figure out an estimate to the distance to this object and its speed. So first of all, let's look at what we can tell from the image. From the image, we can see that from about here to there looks like it's about 2.5 arc minutes. Okay. So that's the angular size, and if we want to measure the distance if I want to know the distance to something, I draw the standard picture that we have that looks like this, where we have, if we know the angular size and the actual size, and we have the distance, that these things are all related, and we imagine again that we are in the center of a circle with the radius of the distance to this actual object. It's always good to draw this picture whenever you do it, although it may seem redundant at sometimes. This angle here is the 2.5 arc minutes that we're seeing in this picture. Okay, we're going to make the assumption that the actual size is the same size as the Milky Way galaxy, and that's about 100,000 light years across, and we're going to want to find the distance. And we know that they are related with doing the ratios. A over 360 degrees, so the angular size over 360 is equal to the actual size over 2 pi times the distance. Okay, so moving down just to give myself a little more space, that means that the distance is equal to, just bringing things over, we have 100,000 light years over 2 pi, and the other side gets inverted, so times 360 degrees over 2.5 arc minutes, and then we have to make sure to, in the denominator here, to convert between the arc minutes, 60 arc minutes in 1 degree. Okay, and you do that calculation. Notice the units, the arc minutes cancels arc minutes, degrees cancel with degrees, and we are left with light years here. So the result is going to be in light years, and I get 1.4 times 10 to the 8 light years, which is the same as saying 140 mega light years away. So that's our distance to this object. Again, a ghastly distance. It's very, very far. Now, let's look at the speed. So we're going to go back up and look at the spectrum. Now, we know that there's a lot of hydrogen in this galaxy, and we're expecting a bump at the hydrogen line. The hydrogen line is here at about 656 nanometers. Unfortunately, what we actually see is the peak is here at what looks to me about maybe 662 nanometers, and it's shifted. So essentially this is the hydrogen line, but it's shifted towards longer wavelengths, which means this is more towards the red end in this, and this means if it's shifted this way, that means it's moving away from us, so which is moving to the longer wavelengths, and we can figure out the actual speed because these are light waves, and pretty much the rule is for the Doppler shift, the percent change in the wavelength is equal to the translates to is resulting in the speed of the percentage of the speed of light. So for example, if we had a 10% shift in the observed spectrum, we would see that this object was moving away from us at 10% of the speed of light. If it was a 15% shift, we'd see a 15% shift, and so on. We're not going to see such large shifts. So the percent shift is simply, if we just kind of scroll down here, what we have is we have 662 nanometers minus 656 nanometers compared to 656 nanometers, and I can multiply it by 100%, but I get, with this, I get 0.009 or really 0.9%. Okay, and so this object is moving away from us at 0.9% of the speed of light. Let's figure out what that would actually be. So if I do 0.009 times the speed of light, which is 3 times 10 to the 8 meters per second, that gets me about 2.7 times 10 to the 6 meters per second. Okay, so that's pretty cool. So pretty much we can get the speed, and it's going away, and the distance. Now, as one final interesting point, we can say how long at this distance away from us, if we kind of reverse the movie, so then it's coming towards us, if we're kind of reversing time, and how long going at this speed would it take to run back into us. And this is going to be a long conversion, but it stems from pretty much the fact that speed is equal to distance over time, which means that time is equal to distance over the speed. And so just doing this out, the time that we're taking, so we have time is equal to the distance, which is 140 megalight years, so times 10 to the 6 light years, divided by the speed, which is 2.7 times 10 to the 6 meters per second. Now I'm going to do a whole bunch of conversions to get it to get the units to match. So essentially I want the light years to cancel, so I'm going to have get rid of light years here. 1 light year is 10 to the 16 meters, and then I also want to convert the per second down here into something like years, so that's going to come out in years. So let's do that. So seconds to minutes, minutes to hours, hours to days, days to years. And notice it's actually going to get flipped up on the top, so the answer is actually going to be in years. And so I have 60 seconds in 1 minute, 60 minutes in 1 hour, 24 hours, in 1 day, and 365 days in 1 year. Notice the units, just kind of doing this. Meters is going to cancel with meters. Light years is going to cancel with light years. Seconds with seconds. Minutes with minutes. Hours with hours. Days with days. And the 1 over year is going to be a year. So the units check out. Going through the calculation, it helps do all the bottom first and then all of the top. And at the end, we get about 1.6 times 10 to the 10 years, or another way of putting it is about 16 billion years, which is approximately the age of the universe. So what we have is the last time this galaxy was on top of us was the beginning of the universe.